this GHC Core for many years, system F omega, which we're talking about, and algebraic data types. So just I will show you simple example of that. So let's say we have this example in Haskell with algebraic data type. Very simple. For points, we have type for points with two, like x coordinate and y coordinate. Then we have accessor function again, which is not inlined, just in order to see it in GHC Core. And then this is a simple program to be able to compile it. So we'd like to have 2 as a result, 2 printed as a result of running this program. And our goal is to see how we can translate all that stuff into GHC Core. So it's not system F omega because of these algebraic data types, and we have these algebraic data types in the GHC Core. So here they are. So this is xCord function, and you just see that you can use this point x in the type system. So you just add them to the type system. And then this is data constructor, and you can use it as it is. So it's an extension which gives you an ability to use data types, algebraic data types in your GHC Core programs. So system F omega with these algebraic data constructors, and that's it. Nothing more. And then this is a usual system of omega tools with type application and value application. And here we have big lambda and small lambda for values. So everything as usual. All right. So in that period, GHC Core looked like this. We had 2 different lambdas, big lambda and small lambda for types and for values. We had 2 type applications, and we had no other things. So this was for all time, like for 20 years, we had this GHC Core. But then we had to extend it. And the first and the biggest extension of this GHC Core was introducing of algebraic data types and associated types. And the system we come up with was system FC. Actual story is a little bit different. So this paper of Peter Jones and others in 2006, it introduced generalized abstract data types. Then there were some problems with it, with this notion of data types, and then they've come up with other implementation in another paper of 2009. And the main problems were about type checking. As you know, type checking is not our problem, because type checking is done before we desugar everything to GHC Core. And the first attempt was to extend GHC Core with algebraic data types. I will say several words about what is generalized abstract algebraic data types. In fact, it's quite a difficult concept. You can do a lot of things with it, but it's not our goal here to learn how to program with GADT. Technically, it is very simple. So in this data type for expressions, you can have different types for different constructors of data, for different data constructors. In usual algebraic data types, you are forced to have the same type for every data constructor. For example, in maybe A, you have nothing of type maybe A, and you have just something of type maybe A. It's impossible to have for one data constructor result like maybe A, for another maybe int, and something like that. But generalized algebraic data types, they allow you to use different types there. So like this one. So we have expressions, they can be either natural numbers, like this expression of type int, and they can be also pairs. So sometimes you have pairs as a result, sometimes you have natural numbers. And these data types, so again, the only difference, in usual data types you should have the same type as here, XA, 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 in all the data constructors. But if you want to have different types, then it's GADT. So that's technical difference. Only one technical difference. There are no others. And these GADTs, they allow you to write functions like this one. They're very expressive. You can evaluate expression which is parameterized with type A, and then you get a value of type A. And depending on the data constructor, you can return values of different types. For example, if you have 0, then you evaluate it as 0, which is of int type. If you have this successor, then again you can evaluate it as this type int. But if you have a pair, then you can evaluate it as a pair. Well, that's quite interesting function for Haskell. So different clauses, different parts of definition of this function, they can give you different types. Sometimes it's integers, sometimes it's pairs. And you can use it in functions like that. Do you see the type for res result variable here? Can you infer it by yourself? What is it? What is the type of this? Pair of two ints. Pair of two ints. It should be like that. So it should be something like that. Yeah. We've applied eval function several times, and then we can come up with this with resulting type. The first implementation of algebraic GADT was to add this ability to the GHC core, just to have different types for data constructors. And then they implemented that. But this extending was not a very good idea, because GHC core, after this introduction of GADTs, becomes very difficult for evaluation. And it was very, very inefficient. And in 3 years, they come up with an idea to remove GADTs from the GHC core. And in fact, they found one small point which was enough to extend GHC core. So there was no need to add the whole GADT there. And this only one thing, it was very simple. Let's see this idea. So it was given in the paper of 1907, and then it was completely rewritten because there were too many mistakes in that paper. So they just completely rewrite it, and now we use the result of the later paper. So here is the idea. So you have a context with two types. So in general, you had exp A, and in one particular clause of function definition, you should have exp int. So the idea is to say somehow that A in this clause is the same as int. So they should be the same in this clause. And in other clause, A should be the same as the pair of B and C. So this idea being the same type, or they use the word coercible. So the same types, we call them coercible to each other. So that's an idea. So in this context, you have A is coercible to int. In that context, you have A coercible to a pair of B and C, for example. The idea is to bring coercion as some evidence of this coercibility to the context. It's just something that you add to the context. Some evidence that two types are the same in this code. And if you have this coercion, so this evidence that they are the same, then you can cast one type to another. So that's it. So if you know that in this context a is the same as int, and you have a variable of type int, then you can safely cast it to the type a. And casting here means doing nothing, actually. So you just allow your type system to know that these types are the same. You can use the value of this type in a context which require the value of different type, because they are coercible. Let's go back to this example. So look, that now we have algebraic data type without any generalization, because here you see result xa here, xp here, xa here. So the type for all the constructors is the same. But you have this constraint, which is type constraint. So in this constructor, you say, well, a should be coercible to int. And then type is xa. Here again, a is coercible to int, and type is again xa. And here a is coercible to pair of b and c, and the result is still a. So one simple addition of these coercions gives you an ability to implement generalized abstract data types in terms of algebraic data types. So you don't need anything else from generalized algebraic data types besides this idea of coercibility of two types to each other. But just you have to use this additional argument. And look, we use this double arrow here to denote that this is in fact a type. It's not a value. It's a type argument. So we use it for constraints, for type classes normally in Haskell. But here we use this type argument for this coercion. So it's some sort of a type here. For example, here have simple function which returns 0, and we know that 0 should have a type here, so it's additional argument to 0. And what do you think? How to prove that? So now we have to provide this type. If you have two arguments, you have to provide both of them. So now 0 should have one additional argument, type argument here, so you have to provide it. So how can you come up with this new type? So how to prove that this is the right value? So what do you need here, actually? Which coercion you need? What should be coercible to what?
A is int. It's reference.
There is no a here.
Int is int.
It should be int is coercible to int, actually. Because your goal is to prove that the result is int. But you know, so it's not xa anymore. You need a value of type x int. And here you have int is coercible to int. So that's exactly reflexivity. So in Haskell, we don't use this term reflexivity for that. But we just use type itself as an evidence of coercibility to itself. So if you say, well, just int is an evidence that int can be coerced to int. That's what they do. But technically, it's just reflexivity. So that's what you need to compile this code. And this is example of eval function in its core form, in its GHC core form. Let's find this how to read this. So we have big lambda for type here. We have small lambda for our expression. And then we have case expression on X. So we don't use pattern matching in the GHC core. It's just case expressions, and every pattern matching is actually compiled into these case expressions. And here you see that in GHC core you have this argument explicit. Remember that in GHC core every argument, every type is explicit. So this coercion is explicit too. So you have this part, it's an argument of 0, and then you have this part. And this is quite difficult. So in evaluation, you have to return 0. 0 has type integer. But what should be result here, the result of this computation? It should have type A. So you have a value of type int, and you need a value of type A. And you coerce that you can do cast here using this operation. So this will be cast. Again, it's not runtime computation. It's actually type level computation. You do that for type checking. What we're using here? Well, we're using cast operator, and it is defined as follows. It takes this equality, and then it casts to the right hand side of that equality. So here what should we do? We should take this 0 and we should cast it to int. So we need coercion. No, we have 0 of type int, and we have to cast it to A. So we need a coercion int coercible to A. And we have another coercion here. A is coercible to int. And we just use symmetricity here to just turn around this coercion. And that's an operator here, so it's just a function. And compiler is able to come up with this by itself. So we did not do that in our Haskell code. So when desugaring this code, compiler is able to come up with this proof that A is actually coercible to int, or int is coercible to A. Because it has this in the context, it is able to come up with this symmetry, and then it has this symco will be int is coercible to A, right hand side is A, and then 0 is cast to A. And now it has the correct type. So we did not have something like that in our Haskell source code, but then desugarer finds out that, well, there is a proof, and it can actually be converted to this GHC core where everything is explicit. So please ask me a question here, because it's really hard part of it. So we had Haskell source code in the beginning, and then we've desugared to GHC core. Well, yeah, they are doing something like that there. Yeah, right. Yeah.
So these are, I mean, it's solved. I'm assuming that this is really a constraint. Like it's actually a constraint that the solver solves.
Right.
The same way it solves everything. There's pre-baked things in the compiler like A tilde A for any A. And
it's also part of our typing system. So we just add this as an axioms. So.
But why? Like, I guess what I don't understand is why do you still need it? Why is it that we still need this at core? To the point where, like, you need to provide a proof at core time that this thing is what it says it is. Like, why can't you just assert that? Like, if you have a proof, why does core care? Like, you wrote simco here, like it's actually there's a representation of this.
Because this language should be typed.
Yeah, I understand putting the result thing, but like, what does core do with the proof simco?
It does nothing.
Okay.
It will after we have this proof, we'll erase it, undoubtedly. We'll never see it again. But while we're working with core, and while we simplify it, while we optimize it somehow, we need this guarantee that it will still be type checked.
So this guarantee could also be like explicit annotation of, I guess, like, maybe I would need to just look at later, like more examples of like how it would perform such a, like why, when it would come up again, that it's important that we somehow carry this proof around, rather than just having like a unit type that's like, check this thing is whatever it says.
Yeah, but yeah, we need to do this check very often.
Yeah.
So if you do something with your core language, and these optimizations, they are too many of them. So we want to have guarantee that nothing goes wrong. So we type check, and then we do something, we change this expression somehow, and we want them still to be type checked. So that's a guarantee for us. And then when we are done with optimization, with all that, we just remove all this stuff. We don't need it anymore. But it still works while we're doing things like that. All right, so there is no need to extend GHC Core with generalized algebraic data types. It's enough only to add these coercions, and that's it. And one question here. Again, why coercion is a type and why it's not a value? And actually, we've answered several times to this question already. We don't need those coercions when in runtime. Don't need them. And for us, we can erase types. And everything that should be erased, we just call them types. That's it. And remember this idea. So when you have dependent types, when you have types depends on values, sometimes you want to erase some values too, and not just types. And this question of erasing becomes very difficult there. So some values can be erased, some values cannot be erased, and so it's a very interesting question when it goes to the dependent types. All right. In fact, this coercion can be used for absolutely different things too. Here's associated types that were introduced in 2005, and in fact they were developed even further. And type families, they are just the same paper. Actually, they were introduced right there. But associated types is as follows. So you can have types which reside inside type class. For example, here, so you have to define type class for collection. And if you have a collection, then you have a type of element. And associated types can give you type of an element which depends on the type of the collection. So here you have this. So you can see, look at this as a function from C type of collection to the type of element. It's like a function over types here. And then for inserting things, for example, you have to provide some value of a type which can be inserted into this collection. And it should be type of the elements of this collection. And you cannot insert something different. And for example, if you have this collection as a list of E, then type of elements will be E, naturally. And for example, if you want to define collection of bit set, then you want to say, well, element of this set is just a char. Maybe you can use char for zeros and ones, for example. So this will be just type of element. Doesn't matter. But these are different instances. So instances give you several definitions for this type function lm. So depending on the type of collection, you can come up with different types for elements. And now the question. Here is the code. Code which use those type classes and instances. What is the type of X here? Well, definitely it should be char, because we are inserting into bit set and the type of elements is a char. But when you look at the type of insert function, it's not char. You see? It's something like LMC. So you have to provide not a char, but something of this type. And again, it's a point where you can use coercions. You can say that this char is exactly the type LMC. So you have two types which are coercible to each other in this particular function call. So how we can do that? This is an algorithm for implementing classes, type classes at instances in GHC Core. It's very well-known algorithm. So we have no type classes in GHC Core, and instead we are doing this translation. So every type class is actually translated into a record. Record like algebraic data types with just one constructor. Or we also call it a dictionary of methods of this type class. Every class method becomes just one field in this record. So if you have like show type class, then you will have a record with one field show. They have some other, I think in show type class they have other methods too, but show will work here. Instance is one value of this dictionary. So instance for integers will be one dictionary, one record. Instance for strings will be another record. Instance for, I don't know, some other types can be another record. And instance is just a value. So it's just one particular record with some particular fields. And if your function depends on some type class, you just, when you run it, you just provide with one specific argument. And that's it. So this argument is just a dictionary. In fact, do you remember those f show integer stuff in the translation? Never asked me about it. They were just, so in the call to print, in the call to plus, we had this argument f show integer or f num integer. These are just these dictionaries, these records. So instances that were given as an arguments to the functions. One problem here with this translation is that records cannot contain types. And that means that we have these chars and LMC and their types, and we cannot put these associated types into the record. So we cannot put it because it's not a value, it's a type. So we have two options as usually. We can extend our GHC core with an ability to keep these types in the record. Another option is not to extend core, but instead to encode somehow this dependency in terms of this core. We are doing this as follows. So let's see. And this is, again, we will use coercions for that. So this is our associated type here in this class. So we've seen this definition before. Then we add function over types here. You know that function over types is not a problem for us because we have system f omega. And functions over types is just all right there. So we can do that very easily. By the way, in that time we may not have these type level functions in Haskell itself, but it was always possible to have them in GHC Core because we have system f omega. And that's what we've discussed before that. So we had type level computation, any type level computation with these functions over types in GHC Core right, forever. And we did not have them in Haskell itself. So GHC Core for a long time was much more expressive than Haskell. Well, and it's simpler and it's more expressive because it's good theory behind it. So we can translate it very easily, just type level function, no problem for system f omega. And then for every such instance, we just add so-called coercion axiom. So if we have this particular instance available in our code, then every such instance creates such axiom. So it says that this function lm for bit sets is actually coercible to char. If you have another instance with another definition, then you will have another axiom. And these axioms, they just fly around when you, so they combine your environment for your core expression actually. And algorithm of type checking can use it. Well, it looks, well, I need something like that. Let's see how, do I have such axiom in the environment? Well, I see it. So then it can use this axiom for proving things. And now this dictionary for instance is just as before. Nothing special here. Just dictionary with implementation of every function, usual value without any additional things. So we had this associated function. It becomes function over types in GHC Core, and every instance with a definition for this function becomes just one axiom. 10 instances, 10 axioms. That's it. And now how we compile this code into GHC Core. This is our Haskell. And this is GHC Core in Haskell. And look, this additional argument. We have x, which is clearly has type char, but we need not a char. We need lm of bit set here. And we can cast x, this char, to lm of bit set using this symmetry and using this axiom. Just again, this cast operator, it casts to the right-hand side. So axiom has char in the right-hand side, but we need opposite direction. We have a char, but we want to coerce it into lm bit set. So we use symmetry, then it goes around, and then we have char coercible to lm bit set. And then we say, well, this x actually is coercible to lm bit set, so it has this type, and type checker is fully satisfied with this code. So the same feature, one small addition to the GHC Core, it works for both generalized algebraic data types and associated types. Absolutely different. Introduced absolutely differently by different authors, different papers. But they can be implemented using one simple addition to the GHC Core. And this addition was system FC. So it's the first step behind system f omega. FC means system f omega with coercions. And in the paper, when this system was introduced, there are proofs for many, many properties. So these coercions, they were introduced as types, and that means that they can be erased. And these properties, they were proved in that paper of 2007. Also, several operators over coercions were added, like reflexivity with symmetry. And in difficult cases, you have to do several. You can use several coercions at once. You have use symmetry several times. There are also other operators for them. So there is normalization, so you can compute. So technically, it's like some proof system inside this type check. It's inside the sugar, actually. So it should come up with the proof that you actually have something coercible to each other. It's rather simple, but still it's a proof system inside it. And then other things, so axioms were developed, these abstract type constructors that it's actually type level functions like LM, they were introduced in this paper. Progress and preservation were proved for this system of C, so otherwise it would be unwise to use this system in Haskell. So everything is proved. Operational semantics defined, rules how to translate Haskell into this new system. Everything was done in this paper. So just look to the paper if you're interested. Yes?
So implementation-wise, you say it's a simple addition. How expensive is it to implement? Because with all those qualities and symmetries looking up into the context, doesn't it blow up the context enormously, possibly? Or is it...
Well, it takes about 2 years to implement it.
No, I mean not to implement, but kind of what does it affect the performance a lot? So if I use a lot of algebraic data type, for example, or associate type families,
well, all this stuff will be erased anyway, so it doesn't affect performance at all.
I talk about type checking. Kind of, is it how costly is it? You know,
well, it is costly. It is costly, but type checking is done without all these conversions because when you type check Haskell source, and you have to type check these all these constructions, and you have to come up with completely new algorithm of type checking. And for example, for algebraic GADT, the algorithm is called, I think, outside in. So it's absolutely new type inference algorithm, and it's less efficient than what we had before. So in terms of type checking, of course, it's less performant than before. But then you have much more expressive language, usual trade-off. But as for evaluation, there is no problem there. So everything is erased, yes.
Are you saying that there's no type checking done on the core? It's only sort of there in theory that we know that these transformations are valid because they don't change the type.
Well,
we're not actually going to check that.
There is type checking in core, but type checking is explicitly typed language. And that means that type checking there is almost trivial. So we are using type checking for this core in order to get just some guarantee that everything goes well. And that's it. So it's true. When you have all the types specified right there, but it's not a big job to check them.
I think there was no misunderstanding. It was like the proofs were there to be sure that the type system language could be expanded that way. And so the proofs are done at the GHC developer level. They did this, and now they could expand it, and now they could rely on it. Is that the answer?
Pretty much, yeah. Thanks.
All right. So this is purely theoretical paper. If you look at it, it's rather difficult. There are many fractions in there, many Greek in this article, in this paper. But it corresponds very clearly to the Haskell source code. So it was really implemented, and everything works as was expected in this paper. But again, remember that this paper, after it was written and published, and after it was delivered in the conference, it was rewritten from scratch. Because when they started to implement it, very many issues arose. So there were many mistakes. They've decided to completely rewrite it. So remember those phrases about GHC as a laboratory. So you have paper for the conference, and it doesn't work when you come up with real implementation. So if you are good people, then you have to rewrite your paper. Of course, it's impossible to publish it again and to deliver it again at the conference because there was such paper on this topic already. So what they did, they just rewrite this paper and put it online and say to everybody, please don't read that paper. It's wrong. we rewrite it, and now we have new paper, and it's absolutely right because we've implemented it in GHC. So that's the story of type theory research, nowadays.
Isn't that there was a mistake in proof somewhere? Like, how can
Yes.
you go wrong?
Yes, they were mistaken in their proofs. They were mistaken in the several operators which work over these coercions, and there are many other kind of mistakes. So when they implemented it, they decided, well, we don't need this, but we need something else. So in order to implement that, there were problems with translation from Haskell source code into this GHC core. So there were many problems there. So when you write algorithm on paper, then you look at, well, it's quite good algorithm, But when you try to implement it, then lots of issues arise. So that was the case. But GHC helps us. When you actually implement it, you see all these problems, and that's very useful. All right. And now we've come to a very, very interesting point in Haskell GHC development. So after 2 years after implementing this system of C, it was suddenly realized that type system allows very, very bad things. And that's usually a case when you have several features developed independently, but when you use them together, you come up with the problems. So that was the case here. You have paper on one feature, you have paper on another feature, you implement both features in the compiler, and when someone tries to use them together, you have a problem. So let's see this problem. There is a very good extension, very useful extension, generalized new type deriving, which allows you to skip writing boilerplate code. And this is very, very good thing. For example, you have a new type. As usual, new types are used when you want to hide internal representation, but you don't want to be less performant when you actually evaluate this code. So this new type just hides integer behind this data constructor. And as usual with new types, they are removed during computation, during evaluation, and there will be no age there. You will work with int values, but the types will be different. So when you're a programmer, you use age, and you cannot use it interchangeably with ints. They're different types. But when you evaluate them, they are the same types. So no problems with performance, but you are on the safe side because you use different types when you write the program. So let's imagine we have this type class with one function, good over ace. We have one instance for int, which is doing +1. And then, thanks to this extension, you can derive instance for age. Because basically, what is this instance? You should unwrap this age, you get this integer, then you add 1 to it, and then you wrap it again. That's it. And of course, you can derive it very clearly, no problem. So you don't have to write this boilerplate, you don't have to unwrap and wrap it, you just can derive it automatically using this extension. That's fine. You see, it's a good idea to do things like that. It's also good to have such axiom, because, well, age and int, they are the same thing here.
Why would you say that's good?
Well, because they are the same types. Technically, they are the same.
But that's like the whole point of the new type is that they don't have the same type.
Well, they don't have type in Haskell. They don't have the same type in Haskell, but they should have almost the same type in GHC Core. Haskell code is type checked already. You are not use them wrongly. But when you translate them into GHC Core, you want to be as efficient as possible. And in this case, you want to go around quickly between these representations, actually. So when you evaluate things, you want to be them the same thing. So you know that there will be no problem because Haskell source code was type checked already. So you want to be efficient here. So that's why they should be the same using new types.
Is it possible to ever have a version where the two types aren't exactly the same type?
What do you mean two types have?
Well, so the two types on either side of the tilde, can they ever be a different type?
You mean?
Like age and int are the same type.
Yes, and what's the question?
Is it ever possible to have a coercion like this where they're not
So-
actually the same?
So this coercion, well, this coercion comes from this new type definition.
Yes, I'm just asking in general.
So
do this.
you cannot write this in Haskell, this axiom. So this axiom will be added during translation into GHC Core. So they will not be generated freely. You cannot say, well, I'd like to have these two types coercible. They just come up as a result of type checking.
You're hitting on basically the problem that we was about to explain, which is that you have two types which you kind of don't treat the same and you kind of do treat the same, and you can view coercible as these two are the same type at runtime, or you can view it as these two are the same type in that they have the same name, and you can kind of mix those, and then you have really bad results if they're not the same.
But I think we'll see something like that right here. So we have this coercion which comes from the new type definition. And then we have a question. Now we have a functions over type. If age is coercible to int, what about th and tint? Are they coercible to each other or not? So if you are studying basic math, for example, you come up with a question whether this function t is injective or maybe it's not surjective or something like that. Maybe it's a bijection, so it depends on that. But here, in general, you cannot answer this question. So whether they are coercible or not. But when we had this coercion system FC and this extension, for several years, these types th and tint, they were coercible to each other. And that is a problem. And now I show you example which blows Haskell just as a static type checking language. So we will do very awful things using this coercion, th to tint. It's quite difficult example. We don't have much time to talk for a long time for it, but it's a very well-known example. You can find it over the internet, so it's very well known, really. So let's say you have this type level function inspect, which is defined as follows. For age type, it gives you int, and for int types, it gives you bool. Just type level function. You convert one type to another. Then you have this type class bad idea. Well, meaning that it's bad idea. And you want to have this function there. So the argument of type A and result of type inspect A. Then you implement this instance here for integers, and you say, well, bad is equals to greater than 0. That will be a function of bool result of type bool. Because, well, inspect int is bool, so this is bool. So this is type checked without any problem. And then you derive this instance for ages. Deriving instances, that means you will use this deriving with a coercion that age is coercible to int. And now the question. What is the type of this expression? Can you type check this expression? So, well, let's see again here. What is the type of bad MKH5? So which instance is it? So if argument of type H, yes, then it should be instance. This one, yes, this one.
Yeah.
And in this instance, you have type of result inspect H. So it will be integer. You see? So for this instance, it should be integer because we have a type level function and it moves H to integer. So we have this expression of type integer. It should be like that. Then you look at generalized new type deriving. It works in the presence of this axiom that H is coercible to integer. And that means that it will use the same implementation as an implementation of ints, which will be greater than 0. So technically, the result will be bool value as a result of greater than 0. But we'll look at this bool value as if it's an integer value. So your program gives you an integer, which is actually internal representation of a bool. And this was possible for 3 years in GHC Compiler. So just looking at the internal representation of bools, and you see those zeros and ones, how they represented true, how they represented false, and all stuff like that. And this was the result of this, just using two features, generalized new type deriving and system of C with coercions. So again, to completely understand this example, it should take much time. But this was a problem, so we had to fix it somehow. So in general, it's impossible. So if you have integer, then it should be integer. If you have bool, then it should be bool. It's impossible to look at this value using different type. So in memory, you have value of type bool, but you look at it as if it's in. Well, it's like C language.
Yeah, we don't see all the time. So.
Yeah, but in Haskell we shouldn't do that.
Yes.
Oh, at least we should not expect that from Haskell, being able to do things like that. So we can understand that for this particular function, inspect, it's not the case that they are coercible to each other. Inspect H should not be coercible to inspect int. But if you have maybe H and maybe int, for maybe they should be coercible. Because there is nothing strange with maybes. And it behaves differently. So you want to have this generalized new type deriving for maybes, but you don't want to have it for inspect function. So what is the difference between maybe and inspect? Can you see what's the difference?
GAT like result type difference.
So well, in maybe you have result always maybe A,
Yeah, that's what I meant.
and well, it's not what we actually need here.
Like all data constructors are.
So
Yeah.
so what we actually have here, maybe values. We'll see actually the answer on the next slide. So inspect is trying to use its argument, and it looks at its argument, and dependently on the independence of the argument, it gives you different results. So it inspects it really. So if it's integer, then you return bool. If it's H, then it returns int, something like that. So it uses its argument somehow. But maybe is doing nothing with its argument. So the question is when it is okay to use this coercion for these lifted functions. Well, lifted means we have h int and then we add another function there. So when it is okay to do that, when it's not okay. The answer was given in this paper. So System FC 2007 and this paper 2011. So that's basically this time slot when this was possible, before they've come up with the right idea. And the idea of this paper was as follows. So we're using types for different things. Sometimes they just encode something, and sometimes they're providing representation of something. And using these two notions, roles of types, we can have different equalities for types. Nominal equality here is just an equality which we used in Haskell forever. So it's an equality of types with respect to type synonyms, so up to type synonyms. So if you have string and list of chars, then you can use them as the same thing. So it's type synonyms. So if these two types are equal, then that's fine. They are equal. But age and int, they are equal differently. So they're equal in their memory representation, because they both will use representation for integers. But they will be different in terms of nominal equality. So they're nominally different types. And that's very useful for us because we type check and we don't want to use them interchangeably. Another notion which is in use here is parametric and non-parametric type variable occurrences. Parametric is a good thing. That means that we don't depend on this particular value. And non-parametric is a bad thing. It means that we are doing something with this type variable. So let's go over this definition. Let's try to find out by example whether this occurrence of type variable is parametric when it's not parametric. So what do you think about this A here? Is it parametric or non-parametric? It's really parametric because we're not doing anything with this A. What about this one? Well, it's non-parametric because dependently on this A, it can be sometimes age or it can be int. So we are doing some inspection on this type variable. So it depends on something. Again, here, is it parametric? Yeah, it is. List is parametric. Here, we're not inspecting it. We're not inspecting type. Of course, we are inspecting values, but we're not doing something with these types. What about this one? It will be non-parametric because we are not non-parametric here. And in this bad idea type class, it's not parametric either. Because we are using this function inspect, which actually looks at the type of the argument. So some of the occurrences are parametric and some are non-parametric. And this is actually the difference. So sometimes you can use coercion, sometimes you cannot use coercion in these cases. So this is the answer to the problem we've posed before. So if this type variable is parametric, then we're allowed to lift this in the case of representational equality, like in age equal to int. If it's not parametric, we're only allowed to do that with nominal equality. So that's it. So age and int, they are nominally different. And that's why this bad idea type class is wrong. So we should not have to be able to do this lifting for it.